Hey guys, moving on with our study of quadrilaterals. Today we're going to go over trapezoids. It's going to be pretty fun and pretty brief. I hope you guys enjoy it. Trapezoids are pretty simple. The definition is a quadrilateral, means it's got four sides, with only one pair of parallel sides. So we've got one pair of parallel sides instead of two pairs, which would make it a parallelogram. So it's kind of like a distant cousin to the parallelogram, but that didn't stop it. Never mind. Moving on. So we have one set of parallel lines, which means we have two pairs of same side interior angles. So these two angles A and B would be same side interior, and these two angles C and D would also be same side interior. Now they're not necessarily going to be related to each other in any way because the other two sides aren't parallel, but the transversals that are forming those would form two different sets of same side interior angles. So this transversal and this transversal over here. Yeah, so if, for instance, A was 60 degrees, then the supplement of that would be B, which would be 120 degrees. Now, that doesn't change what these are going to be. It doesn't impact them at all. And so I actually couldn't solve for the other side because I don't know anything about that transversal. But if I told you this angle here was 130, then I could find its supplement, which would be the same side interior one down here, which would be 50 degrees. Okay, kind of cool. There are two different types of trapezoids. We have just a trapezoid that has no special name. Then we have an isosceles trapezoid. Now, an isosceles trapezoid, just like an isosceles triangle, is when we have two sides, or two lateral sides is what we call them here. The parallel sides we usually call the bases, and then the lateral sides are going to be the other two non-parallel sides. Anyway, or the transversals, whatever. Those are going to be isosceles if those two are congruent. And the same properties that hold true with an isosceles triangle is the same property that happens with an isosceles trapezoid. Namely, that if the two sides that are equal, say these are both the small sides, meaning the opposite angles, both have to be the smallest angles. And they're going to be congruent, right? That's the base angle theorem. We've proven it 100 bajillion times in about 4 different ways, actually 3. But you get the idea, right? So if these two sides are the same and this base angle is A, that means the opposite one over here, not the opposite one, but the other base angle has to be A as well. Then if you remember on our parallelograms, the opposite angles were congruent because they were supplementary. So we had same side interior, then these two were same side interior, so made both of these B. And then the same side interior for B would be this one up here, which would be A. So the pattern that we had for parallelograms, and this is what we have for isosceles triangles. Now if we kind of put those two together, we can actually figure out what the properties of isosceles trapezoids are. So here we have a trapezoid, because we only have one set of parallel lines, and it's isosceles because both the opposite sides are the same. And we want to figure out what these angles up here and here are. You can probably guess if this is A and B what those two are, but let's actually prove it. So what I'm going to do is I'm actually going to swing it in. So I'm going to swing this in, which we kind of said was not enough, right? It could be a trap, right? That whole thing that I've shown you a bajillion times as well. Well, once I do that, now it actually is a parallelogram if I'm looking at the red line. And if it is a parallelogram, it's really the same thing as this. So we have same side interior, which means this has to be the supplement of A, which is B in this game, the same supplement of A we have up here, that's B. And then if this is B, the supplement of B is A, right? Okay. And if this is A, oh, look at that shape. Doesn't it look just like that isosceles triangle? It is. So the base angles are congruent. So if that's A, this one over here has to be A as well. So look at the big picture of this isosceles trapezoid here, the big one. The base angle A is the same base angle we have to have over here. And we use the properties of isosceles triangles and parallelograms. Isn't geometry just the best? All right, same thing we're going to do on this, but now we're going to solve for B. And if the base angle up here is B, well, we know this one has to be B as well. And, well, it's got to be a supplement of A, so it has to be B. Well, let's do it a different way because it's kind of fun. So I'm going to swing this one out here. Oops, spoilers. That one's A. Well, and when I do, that gives me the big parallelogram, and the opposite angle is A, just like it was up here, right? So that's A. Oh, we have an upside down isosceles triangle, so just kidding. I could rotate my whole. That would be funny. Okay, so now you can see it's clearly upside down, right? Or am I upside down? All right, so the base angles are both going to be A, and then from there, the supplement of A we said was B, so it's right back to where we started. So the base angles on the top are B, and the base angles on the bottom are B as well. And this can actually be shown in GeoGebra that we have two same side interior angles. So these two are going to be supplementary, and these two are supplementary as well. No matter how I move my isosceles, that is so cool. Whoa! No matter how I move it, they're always going to have two pairs of same side interior angles. Now, they're not necessarily base angles going to be congruent unless it's an isosceles trap, which I can try to do my best. That's close-ish. Whatever. You get the idea. I'll show you that on another construction, actually. All right, so here's our hierarchy of quadrilaterals, our family tree. We talk about general quadrilaterals, kites that have no parallels, parallelograms have 2 parallels, trapezoid only has 1. We talked about the rhombus and their special diagonals, and the diagonals of a rectangle that's special, and the square and how it's like everything. Well, with the trapezoids, we have a special one called an isosceles trapezoid, and there is something about those diagonals. And if you looked at them, what looks special about them? Well, they're not perpendicular like rhombus's diagonals. They don't cut the angles in half clearly like rhombus's diagonals either, or kites, but they are congruent. They have the same length, and that is a property that actually comes from the rectangle. So I don't know how to explain what's going on with this jacked up family tree, but let's prove it first, and we'll get back to that in just a minute. All right, so the first thing is we have 2 diagonals, the green and the blue. We know if it's isosceles, we know that the opposite sides are going to be congruent, and we also know this side is the same side for both of those triangles. If you can't see triangles, I'm going to pull this one down here so that you can see it better. Okay, cool. All right, so now that we have it here, that side's the same as that one, so I'm going to go ahead and mark it on the triangle here, and that side is the same as that one as well. So we have our green triangle, and then we have our blue triangle over here. The other thing we know is that those base angles were congruent. Remember, we proved that before. So this angle is going to be the exact same as that angle up there for the blue one. So then by side angle side, I guess I'll mark that for you. I don't think I actually like constructed it, but you get the idea. So by side angle side, both of those triangles are congruent, which means their longest side, opposite the biggest angle here, their diagonals, in other words, both have to be the same. So the green diagonal and the blue diagonal are corresponding parts of congruent triangles, which are congruent to each other, and so therefore the diagonals are congruent. Now that property comes from the rectangle. The baby daddy rectangle, which apparently you got your baby daddy rectangle, you got your baby mama rhombus, and then they have the square. And it's some real Luke and Leia stuff going on here because they both came from the parallelogram. It's like, I hope they didn't know, but you never really know. But even worse than that no good baby daddy rectangle is the fact that he had a trap on the side. And with him and the trap on the side, they had the isosceles trapezoid. So it's just, there's the quadrilaterals ancestral ways are they're so messed up, and you thought your family had problems, but compared to the quadrilaterals, you guys are doing all right. So you thought 2020 was bad, not as bad as this. And if you thought it gets worse, yeah, it gets worse. There's something going on. That'll be a video for tomorrow. I am so sorry that I have to be the one to tell you these things, but the good news is you'll never forget all the properties of quadrilaterals because of the controversy, and it makes it memorable. All right, one more thing I have to teach you about trapezoids is pretty simple and fun, is the mid-segments. The mid-segments, that should be capitalized. It bugs me. I have to fix it now. We're good. All right, so mid-segments are going to be segments that are connected from the midpoints of the 2 sides. Now, they don't necessarily have to be an isosceles trapezoid. This is true for all trapezoids. But whenever we connect the midpoints and make the mid-segment, the length of the mid-segment, well, clearly it has to be something between 10, the smallest base, and 14, the biggest base. But what is it? Is it 11? Is it 12, 12 and a half, 13, 13.75? If you took a guess, if these are the half distances, it's actually going to split it in half, and so it would be the average. So what we do is add them together, so 10 plus 10, or base 1 plus base 2, divided by 2, which would be basically an average, right? So the mid-segment is the average length of the bases. So this side here would be equal to 12. Pretty simple. So I will show you the mid-segments are the average of the bases with GeoGebra. So I construct this where you have one pair of parallel lines, and then this is the midpoints. Connecting those midpoints is the mid-segment, which is in green, kind of matching there. And as I move my triangle around, at all times, it will be exactly half the length, or the average length, sorry, of the other 2. Even this is a trapezoid. Wow. Technically. Oh, what a weird, funky trapezoid. All of them. And it doesn't matter what it is. Even if it was, I don't know, this. Upside down. Doesn't matter. It's still exactly half. Kind of fun. I'm just playing now. All right, mid-segments. Okay, so what if you have the average and you have one of the bases, but you need to find the other base? Well, we're like thinking backwards, and so I made this model, which is fun. It was a lot of fun. I don't teach elementary age math, but if I did, this is how I do it. So we know the average is 10. So it's like our balancing beam here is balanced at 10. And on one side we have 16, which on the number line is 6 away. So this is like plus 6, right? So then how far, if it was the same weight, so it's like a weighted average, but it's the same weight, right? Then how far would I have to go in the other direction in order to make it balance? So obviously we're too far right now. So on the number line, is it 2? Is it 3? Is it 4? This is so cool. Anyway, so if we added 6 to one side, right, then what do we do to the other side to keep the average still centered at 10? Well, we would simply subtract 6 from from that side as well. Not both sides. I'm used to doing algebra. So 10 minus 6 would leave us at 4. So when this is at 4, those are equidistant from the center. And if it's a weighted average and they're the same weights like they are here, then that would work. So this value here has to be equal to 4. Which is kind of cool. You could also plug it into the formula, which is not a problem. Okay, cool. 11 minutes in, not too bad. Flying through this stuff. The kite one tomorrow will be pretty fast too. So we did all the harder lessons with our parallelograms and our special parallelograms in class. I'm going to do the easier stuff at home, like the traps and the kites. So, just like an isosceles triangles, the base angles of an isosceles trapezoid are going to be congruent to each other. Trapezoids also have one pair of parallel lines. Those lines form two pairs of same side interior angles, or SSI angles, supplementary, however you want to say it, that add up to 180 degrees. Use the properties to find the measures numbered. So do look here, find which ones are bases and your lateral sides. In this case, I think 1 through whatever, the whole first section there, they're all going to be isosceles trapezoids, okay? We'll get to that on the last one real quick here. So if they're isosceles trapezoid, we know their base angles are going to be congruent. So if this is 96, the base angle over here has to be 96 as well. So those are opposites of our congruent sides, okay? And then 2 is going to be same side interior with that one. So the supplement of 96 is going to give us 84. So those will be your 2 answers there. All right, same thing with number 6, but on this one, if you see in our answers, it said that it was okay, if you see in the instructions, it said it was isosceles. I just forgot to mark the diagrams. If you want to go ahead and mark that, I really should have remade it, because look at those pixelated. I know, I'm embarrassed, but whatever. It is what it is. I can only do so much in a year. So the bases are going to be the same. So the 74 is the same 74 over here, and then 2 would be same side interior with that would be the supplement, which is 106. All right, number 7, these are non-isosceles now. So trapezoids will have one pair of parallel lines that form 2 pairs of same side interior angles. We know all SSI angles must be supplementary, which means they add up to 180 degrees. So on this one, notice these 2 are the ones that are going to be same side interior, not these 2, because those are not parallel. So make sure you pick the right 2. Just look for your parallel lines, your bases, and then work along the laterals, which is your transversal, sorry. So the supplement of 81 is not, we're not looking for the supplement of 95, it's the supplement of 81. The supplement of 95 would go over there. So the supplement of 81 is going to be, let's see, 99? Okay, so do make sure that you pick the right ones, and on the test I would give you the extra one just in case you accidentally did it wrong. All right, number 10, we got 2 angles. Oh my goodness. Those 2 aren't supplementary, so these have to. I'm just kidding. All right, so those are parallel lines, the transversals here, so that has to be same side interior. The supplement of 142 is going to be, what, 38? Yeah, 38. Boom, got it. 13, find the values of the variables of the isosceles trapezoid. Okay, well, it is isosceles, and they tell us the lateral sides are congruent, which means that these 2 have to be equal, so you just set them equal to each other. So 3x minus 3 has to be equal to x plus 5. I'm not going to solve it for you because I'm lazy, but I set it up for you. You're welcome. So then just solve from there. Then plug it in. All right, determine whether it's true or false. If it's false, change the statement so that it's true. A trapezoid has 4 pairs of consecutive angles that are supplementary. Well, on a trapezoid, because we only have 2 sets of same side interior angles, the other 2 are not going to be consecutive angles that are supplementary. We don't know how they're related, so because it's not a parallelogram. So this statement would be true for a parallelogram because they have 4 sets of consecutive same side interior angles. But for a trapezoid, we only have 2 pairs of consecutive angles that are same side interior. So this statement would be false, and we correct it by changing 4 to 2. Mid-segment of a trapezoid is the blank length of the trapezoid's bases. Well, if we add them together, divide by 2, we're taking the average. So it is the average. So just find the mid-segment. All right, so add them together, which is 7.5, right? Divided by 2, which would be 3.75. So pretty simple. Now it gets a little weird because we're dealing with expressions and you can't just add them together and divide it by 2. So you got to set up the equation. Now here's our original equation, but to make this easier, I modified our formula. So instead of taking the sum of the bases divided by 2, because these are expressions, they won't divide necessarily evenly, I'm going to multiply both sides by 2. So I'm going to multiply this side by 2 and then that side over there by 2. And whenever I do that, these are going to like cancel each other out or go away, leaving me with 2 times the midsegment's length is equal to the sum of the bases, which is a formula that's a whole lot easier to work with. So that's what we're going to end up doing. So 2 times that, and I think that one goes away. Yeah, so that's what your formula is going to be. 2 times the midsegment is equal to the sum of the bases. So that's what I want you to use for this one. So 2 times the midsegment, well, midsegment on this one is x, so that's just 2x, not bad, is equal to the bases added together. So that's going to be x minus 6 and 2x minus 9. We can combine all the like terms on the same side of the equal sign. That's going to leave us with 3x's minus 15. And then I'm going to subtract the smaller number of x's so I don't have a negative. You could do the negative, and if you subtracted 3x, you get negative x is negative 15, so then x is equal to 15. Spoilers. But if you don't like negatives, or if you're afraid you're going to make a mistake, just do the other way. It is a little longer, though. So subtract 2x from both sides, leaving us with, well, what's 2x minus 2x? Absolutely nothing. So 0 is equal to 1x minus 15. Then we add 15 to both sides, leaving us with 15 is equal to x. All right, so now we have x is 15. We can plug it in. 15 minus 6 is 9, and then 30 minus 9 is 21. And in case you're wondering, the average of 9 and 21 is equal to 15, because that would be 30, and half of 30 is, sure enough, 15. Cool, so we know we did it right. Number 24. So we'll do another one of these because they're a little bit tricky. So we're going to do 2 times the midsegment, which is 2 times 2x plus 1, is equal to the sum of the bases, so x plus 4x minus 2. We can combine our like terms, leaving us with 5x minus 2. But here we need to distribute through the parentheses. So we're going to do that. That'll look nice. So that's going to be 4x plus 2. Then we're going to subtract the 4x from both sides because it's a smaller number of x's, and leaving us with 2 is equal to x minus 2. Then we add 2 to both sides, leaving us with 4 is equal to x. All right, so x is equal to 4. Then we can plug it in. So that's going to be 8 plus 1, which would be 9. And then 4 times 4 is 16, minus 2 is 14. Ooh, that should be 14, shouldn't it? Yeah, that is 14. Okay, oops. Someone can't do mental math. And then double check our work. We have 4, and then this one was 9, and this one was 14. And if we take the average, that's 18. Half of 18 is 9. So yes, we did do it right. Okay, cool. I do have to fix that later. All right, 29. So if we have a trapezoid where the mid segment is 16, what are the possible lengths of the bases? Well, so if the average is 16, we're kind of working backwards. One way you could do it is like if I subtracted 2 from it, that would give me 14. So if I subtracted 2 from one side, I have to add 2 to the other just to keep it balanced, so the average is still at 16 in the middle. That would give us 18. So it could be 14 and 18. Another one that would be kind of fun, well, just think of it. So just subtract or add the same amount to both sides and come up with another one. But the general rule, which is kind of cool, if this is x and this is y, if you remember from our formula, 2 times the base is equal to the sum of the sum of the base is equal to 2 times the mid segment. So 2 times 16 would be 32. Meaning x and y, you just have to add up to 32. So pick any two numbers that add up to 32. You could even do numbers like 0 plus 32 is equal to 32. And if you think about it, what shape would that make? If you had a side length from a trapezoid that was 0, well, that would be a side length of 0. So if we had a mid segment that was going across a triangle, one of the sides would be 0 and the other side would be 32. And then the mid segment's length, if this was cutting in half, sure enough, the mid-segment's length would be 16, which is really stinking cool. It's actually called a side-splitting theorem. We haven't gotten to it yet, but these two are going to be side angle side because they have the same angle here and the same proportional sides here because they're just half the length. So these two triangles would actually be similar to each other, by side angle side similarity. Now again, we haven't gotten to that yet, but that is where we're going in the next unit, which is going to be fascinating, with the side splitting theorem is what we call it, and it's kind of related to this. So just thought I'd give you a little preview there. So here's our quadrilateral family tree. And over here, I graphed out, this is actually the construction. So you can see this triangle was constructed to be the same length. BF is the same length as AC. So as I change the length of AC, it's going to change the radius of the circle. And where those intersect here is going to actually form the other line. So if I did this one, it would be a parallelogram. But if I do it on the other side, it's an isosceles trapezoid, which is pretty sneaking fascinating. So you can kind of see both of those construction going on at the same time. Love GeoGebra, and I wish we could do some compass work. I am working on getting us new compasses so we can do a lot of compass work, but what I measured here were the lengths of the diagonals, and then you can see as I change all these weird funky isosceles trapezoids that at every single point in time the lengths of the diagonals were always congruent to each other, which was, again, as I said before, a property that came from, unfortunately, the baby daddy rectangle, that good for nothing baby daddy rectangle. I know it is pretty disgusting, but yeah, so that happened. All right, so we're done. I hope you guys enjoy your time off. I really have been I'm feeling a lot better now that I have you guys back in class, and hopefully you guys are feeling better. I'm much more motivated. And so, but if you guys are doing the distance learning stuff at home, just let me know if you need any help. Wish I could see you guys. I guess I'll see you in the halls next year, so that's the only good thing. And I'm still your teacher, and you can still learn from me. And just let me know if you need any help. All right, so see you guys, and have a good day.